Good afternoon, everybody. I'm Ramlal. I'm a PhD student at Chalmers University of Technology, Sweden, and I work on the circumstellar chemistry of AGB stars. And so today I'm going to talk about circumstellar chemistry of carbon-rich AGB stars, but a bit beyond that of the typical star IRC+10216 that you heard a lot about from Marcelino today. And apparently, since we are all in the era of artificial intelligence nowadays, I asked one of these image generating AIs to give me a background image of a telescope looking at an AGB star, molecular emission around an AGB star. And then it gave me something like this. So the star in the top corner, you can see it made kind of well. But then the telescope it gave me was like an optical one with an eyepiece and a lens and stuff. Then I told it, yeah, I see what you're doing, but is it really the kind of telescope we want to look at molecular emission? And then it apologized and drew me a telescope in orbit. And I was like, yeah, I see what you did there. You know your spectroscopy, but just give me something like a dish antenna on a desert or something. And there it is. And I had a few more introduction slides, but I skipped all of them in the interest of time since Marcelino gave you a very detailed introduction into all these things. So basically then we have AGB stars, yes. And we have circumstellar envelopes of dust and gas around these stars with a lot of different molecules and dust formation and many different types of chemistry, including photochemistry and other chemical pathways going on. And the evolution in the AGB is driven by mass laws, as you have heard several times here. And the reason why we want to study AGB stars in particular is because the mass laws which creates the circumstellar envelope, it eventually feeds back all this nucleosynthetically enriched material into the interstellar medium. And this becomes then the forming material for a new generation of stars. So they are a very integral part of the cosmic chemical cycle, I would say. So, and as you already know, there is a chemical classification of these objects into M-type, S-type, and C-type. And we are going to talk today about the C-type stars, whose atmospheric carbon-oxygen ratio is much greater than 1, indicating that they have a lot more carbon, and hence, due to the carbon molecule, it has a lot of more complex molecules and much richer chemistry. So, the story so far about carbon stars is that we seem to know a significant amount about these objects, but most of our knowledge so far comes from this one particular star, IRC+10216 or CW Leo, for very good reasons. In fact, that it's very close to us and it's very bright, and it has a high mass loss rate, meaning that it has a lot of gas in the circumstellar envelope. And this is not to say that other carbon stars have not been observed. Of course, there have been a lot of single-dish observations, as you heard in the talk before lunch. But when we really want to, look at the circumstellar envelope in the era of interferometry, especially, there have been not so many interferometric or spatially resolved observations of other carbon stars. And all these are pictures from mostly Chernicharo and Agundes, and they have done a lot of amazing work on this object, managed to resolve it and spectral scan it and possibly everything you can do with it. And so their work kind of serves as a basis of my PhD as well. And so yes, you can see here that there is also spectral surveys and resolved images. I think you saw the image before as well. So you can see that in a carbon star as well, there is all these spirals and arcs in the circumstellar envelope. These kind of shapes have been studied in more detail for oxygen-rich stars through programs like Atomium. And we can see that in the carbon-rich stars as well. This is very well the case. And so, given that we know this much stuff about IRC+10216 and we generalize it into our knowledge of carbon stars, my PhD is more about looking into more carbon stars, like a larger sample, to see if the conclusions we draw from our study of IRC+10216 in the literature really serves as a archetype model for carbon stars in general. And when we started this PhD, we were really hoping, yes, it would be the case, and turns out to be so. So then what we did is we selected 3 other carbon stars, and these are all selected on the basis that they form a well-defined sample. So together they probe roughly an order of magnitude in mass loss rates, and they also have single dish abundances already in the literature. So this made it easier to get ALMA time, and and so, and none of these objects are also like detached shells or anything. They are typical C-type AGB stars. And then based on our results from this project, we now have a paper out in A&A, which you can check it out if you're interested in sources like this. And so then what we did is we went to ALMA and we got a band 3 spectral survey. We did an unbiased survey, meaning we were not focusing on any specific molecule, but we were just taking everything we can get in the entirety of band 3. And this is spatially resolved with an angular resolution of 1 arcsecond or a bit better in some cases. And you can see here the whole data. So there's a lot of spectral lines you can see. Maybe not as much as we saw in the surveys of IRC+10216 because it's closer and brighter, but you can still see that there is a lot of lines. And for those of you who are interested in spectral scans and stuff, you can be excited about the upcoming wideband upgrade of ALMA, which will make things like this much cheaper and easier. So we are looking forward to that as well. And so what did we find? We detected a total of more than 300 emission lines, and we attributed them to 49 species. And it's safe to say that we caught all the usual suspects, the carbon chains, the silicates, the cyanopolines, the cyanides like HCN, and also the 13C isotope logs of most of these species. So nothing surprising. Typically, we got everything that you would expect from a carbon star at this resolution. And coming to the reason we went for ALMA is because we wanted to really resolve these circumstellar envelopes and see if they look like CW-LEO itself. And seems to be the case. We have mainly 2 different morphologies. Some of the species are centrally peaked. I mean, when I say centrally peaked, I mean within our beam of 1 arcsecond. And you can see these are mostly the parent species like HCN, CS, SIO, CS, and molecules like that. And then you also have the daughter species which are formed outwards in the envelope like CN, in this case, shown here in a shell kind of morphology. And then we also have a bit more complexity in some of the species. So you can see here the color map is HC3N to the left, and then on that is the white contours of SiC2 emission. These are systemic velocity channel maps. So this is in the plane of the sky. And you can see the HNC and C2H on the right as well. And you see that there is all these arcs, and I mean, depending on who you ask, people could also say spiral. And you can also see that there is some central emission. For example, if you look at the HC3 and SiC2 plot on the right, you could see that it's not just a shell with substructure, but there is also some significant emission in the center. And this has been shown to be the case in IRC+10216 as well before. So this is Lewis's paper from 2015, where we see the SiC2 from IRC+10216, and you can see there is a central component as well. But I'm not making a quantitative comparison of the central components itself here because you have to take into account the beams and everything, but just saying that we see roughly similar things. And also, you saw this image from Marcelino earlier. This is the HC3N and C3N. So you can see that the HC3N displays a very similar substructure within its shell in our star and also IRC+10216. So I'm showing this particular star, IRAS15194, because that is the one where we have the most spatial resolution. And so things look relatively same to IRC+10216 as far as the morphology is concerned. And then what we did is we went through every species that we had significant spatial resolution, and we made these azimuthally averaged radial profiles of the emission at systemic velocity. So you just average azimuthally in a line. And from this, we could get the emission extents of the different molecules. So the centrally peaked molecules you can see on the top there, and the shell species, they fall nicely in a shell. And this has also been done for 10 to 16, and this is Agundas 2017. And you could see that we get roughly the same results as them, in the sense that the carbon chains all peak in the same place roughly, and then CN is much farther extended than most of the other species. So we see similar things. And the main reason for making these radial profiles was, along with checking the morphology, of course, was to get some quantitative estimate of the emission regions of different species. So we fit Gaussians to the radial profiles, and from the full width half maximum of these Gaussians, we estimated the emission regions that you can see on the big plot there. And then this is the three colors are the three different stars in our sample. And of course, the yellowish line there shows the star with the least circumstellar density. So it all the molecules fall much more inwards as expected. And then why we want these estimates of the emission regions is because this then allows us to more quantitatively, in a more rigorous way, estimate the molecular abundances. So this is what the single dish observations that I mentioned earlier suffer from, that they do not have a accurate estimate of where the emission is coming from because it's a single dish, and then they have to resort to either assumptions or calculations of photodissociation regions, etc., to then accurately determine the abundances. But now we have observational constraints on the emission regions, and then we went on to do some LTE basic calculations to get some abundances. And you can see here we made population diagrams for several species, and we could get the rotation temperature and column density of the different species from this. And from the column density, we of course then went to molecular abundances, and you can see that we have a large array of species, both parent species and daughter species. And so the red, blue, and green dots, they correspond to our stars, and the yellow circles are abundance values for IRC 10 to 16 from the literature. And we do not see any significant differences, but except for possibly SIO, which appears to be overabundant in our stars. But then this was the first paper that I showed you before, and then now we want to get a more detailed look into the abundances. So we are currently working on some radiative transfer. And so we use the accelerated lambda iteration code, which was developed by Frederick Scheuer and Per Bergman, and then extended by Thaisa here. And it's a 1D spherically symmetric model with a constant mass loss rate and accelerating velocity profile. So we fit Gaussian abundance profiles by using the radial brightness profiles that I showed you earlier and the line intensities. And for this, we need the dust and CO inputs first, which is being done by one of my colleagues at Chalmers. So we do the SED fitting and CO like Monte Carlo radiative transfer, from which we get the mass loss rates and temperature profiles of the gas and dust. And then we put them into the molecular radiative transfer in the ALI code. And I can show you some of the results. So this is currently ongoing work. So I have worked on one of our stars, AI Vol, for CS and SIO. So you can see the line fits for CS here, and we get a abundance and E-falling radius, which are of the abundance profile, which are the free parameters we have. And similarly for SIO as well, we get a relatively good fit. And because we have ALMA data, we can also along with fitting the line intensities, we can also fit the radial profile to include some spatial information there, making the estimates more rigorous in some way. And then just a quick comparison with the literature. So this is the best fit abundance profiles we have for CS and SIO for AI Vol, a carbon star. And you can see here, it's a chemical model from MEDI. And this is a chemically modeled abundance profile for a star of mass loss rate 10 to the minus 5, which is roughly the same as our star. And we can see both from the extent of the profile and the peak abundance that it's roughly consistent. So the only difference is that for our star, the velocity is around 3 times higher. So that would change things a bit. And then also this is for IRC 10 to 16. This is from radiative transfer by Agundas 2012. And here also we can see that both our profiles are very consistent with what we see with CW Leo. So as far as things we have looked into now, till now goes, everything seems to be very consistent with the IRC 10 to 16 results from the literature, which is what we hoped to from the beginning. And so, yes, so we have 3 carbon stars, a lot of lines, and the order of the chemistry in terms of the morphology, and also the abundances, they seem similar to IRC 10 to 16 till now. And we have also plans to use archival ALMA data to go into more carbon stars, so to enlarge the sample even more to probe different mass loss rate regimes than we have right now. And also, since we see the complex morphology, like I showed you before, we also have plans to look into that in more detail about, questions that arise about binarity or the convection regions and things like that with high resolution and different ALMA observations. That is pretty much everything I have for now. Yes, thank you.
Thank you, very nice talk. I have a couple of questions. Once, do you have unidentified lines for these 3 stars in the spectrum?
Yeah, we have 3 unidentified lines, but all of them are very weak.
Oh, yeah, very weak.
Yeah.
Okay. Okay.
There could be, and if I remember correctly, they are also very narrow, so there could be like higher vibrational states of some typical molecules.
Okay. Okay. And the other question is that I think I saw that for CS, SIO, and SIS,
yeah,
you measure the radial extent in the 3 sources, and I think it was systematic that in the previous one, that CS was always the one that extended farther away.
Yes.
And the SIO and SIS look like similar.
Yes.
So this is systematic for the 3 stars, no?
Yes.
Okay.
Yeah,
nice.
That is what we see. We haven't gone into interpreting it much now because the aim of the first part of the PhD was just getting all the data out because it was a lot of data in volume. But yeah, we see that, and once we also get into calculating, more rigorous abundance profiles, we plan to do detailed comparisons with chemical models to see, to try to explain in terms of, physics and chemistry why these profiles are as they seem.
Okay.
Yeah, that is in the works.
We can speak later. Thank you.
Thank you.